Yeah, so today I'm going to talk about how simulator follows dust evolution in their simulations. So we already heard several talks talking about the importance of interstellar dust. Um, dust is providing a very important heating mechanism in the ISM. It's a so-called photoelectric heating by interacting with stellar far UV radiation. Which is actually the most important heat source in most typical spiral galaxies. And also, we know that does provide an ideal place for the formation of molecular hydrogen, which is important not only in the ISM but also presumably also potentially also in the galaxy outflow as well, because people have been proposing that these molecular outflows might be from in situ in galaxy winds. And I also know that does modify the spectrum of galaxies by reprocessing UV light into infrared. Right, however, until very recently, the treatment of dust in simulation, in hydrodynamic simulations for galaxy formation have been very simplified. So the most common way is to simply assume that that, for example, like 40% of your metals is actually in dust form. So that's how people estimate how much dust you have, which is a zeroth order approximation. It may or may not be okay, but this is the simplest thing you can do without following the evolution of dust. But if you look at the observation, you actually realize that the dust-to-gas ratio actually varies not only from galaxy to galaxy, but also within a galaxy. For example, these are observations of the LCM SMC. You can see the dust-to-gas ratio actually scale changes as you go to higher surface density. So it goes to denser area, you have more dust, more metals that is in the dust form. Can be up to a factor of 7 in the case of FNC. So recently, the efforts of really trying to follow how dust evolve and formed in galaxy simulations. Here's an example of the cosmological simulations. You can see here that you can see the total mass here, and then in the lower panel, this is the dust surface density. You can see, first of all, they actually trace the total mass, but then if you look at the dust to metal ratio, you actually realize immediately that this is not really a constant, which is what people have been assumed in the simulation for decades. And in this, simple model adopted in these simulations, they track the destruction. They track several processes. The first is the destruction in the supernova shocks that dust being sputtered by between the collision between gas and dust. And then the dust material is returned back to the gas phase. This is a destruction process, and the second process is follow is the stellar ejecta. So you have AGB stars and the supernova. At the end of their lifetime, they eject the dust. The dust can be condensed in the stellar ejecta. This is potentially a very important source of interstellar dust. But we also know that there's another very important source of dust, which is the accretion in the dense ISM, which is that you can have, once you have some seed of dust, the dust can grow in the ISM just from the collision between gas and dust. So these three are the processes they assumed, and they simply assume that you only have a single grain size, and you can vary the grain size and see how your results are sensitive or not sensitive to your assumption of your grain size. And here's another example that do things slightly more complicated, in a sense that instead of assuming one grain size distribution, they actually take two different sizes. So this is just small dust and large dust with these two values. And in these hydro simulations, they look into the scaling relation between metals and dust, which is basically just the dust to metal ratios. So we know that the dust to metal ratios is roughly a constant at high metallicity, but at low metallicity, this starts to break down. You can see the linear relation breaks down here below around 0.1 solar metallicities. And by following the dust evolution, they can reproduce the observational trend that this break occurs roughly at 0.1 solar metallicity, and this has to do with the importance of the timescale for which the dust, the accretion of dust in the ISM becomes effective at high metallicity. You can also predict the extinction curve for dust evolution models. But for this kind of prediction, you have to have some, you have to assume certain dust grain size distribution. So in this particular case, they track the evolution, not only just the creation and destruction of the dust, the three processes in the previous model, but in this case, they also try to follow the processes that can shuffle the grain size. For example, shattering means that large grains, when you have collisions between dust grains, the large grains can fragment into smaller grains. And coagulation is kind of the opposite process, where you have small grains that stick together and become large grains. So these two processes are important to include if you want to do, if you want to study the evolution of grain size distribution in a self-consistent way. However, one of the limitations of the model of simulation of this kind is that because of the limited resolution of these large cosmological simulations, which typically can only afford roughly like kiloparsec resolution, you really don't resolve the structure of the ISM, so you cannot really follow the dust physics. So the thing that they end up doing is adopting, just like typical galaxy formation simulations, adopting some subgrid models that has certain parameters that you have to fine tune or calibrate in order to kind of reproduce certain observations. And in this way, this is actually in a very similar spirit to semi-analytic models, but the simulation, the galaxy simulation, is kind of in this awkward spot that you have this free parameter, but it's very, very expensive for you to actually calibrate your parameter, because they are too expensive to run many different models to explore the parameter space. For example, that if you have dust extraction in the simulations, what typically you do is like you have this free parameter of the extraction timescale that you just somehow motivated by either like analytic calculations. But these parameters, whether this is universal value, there's no good reason to believe that this is a universal value that can apply, or which particular timescale can suit for all different galaxy population. So what we're trying to do here is try to do ab initio simulations that just focus on a very small patch of galaxy, instead of doing like a full-blown cosmological simulations. In this case, we can really resolve the structure of the ISM such that we can follow this from first principles. So in this particular paper, we try to follow is how dust is destroyed in supernova shocks. The physical mechanism is called sputtering, just collision between gas and dust. And we use this one fluid approach such that the dust is treated as a passive scalar that's just affected with the gas. And the argument for that is that in the ISM, you have magnetic fields, and dust grains are typically charged. And their Lama radius, the gyro radius, it typically is sub-parsec scales, which is smaller than the scale we're considering. It's smaller than the resolution we're doing the simulations. So this can be safely treated as passive scalars. And to actually track the sputtering, there are two different sputterings. One is called thermal sputtering. This is just the thermal motion of gas that collide with the dust. The other one is called non-thermal sputtering. Here, it's just when you have a bulk motion of gas that have a relative bulk motion with respect to the dust grains. This can also give rise to sputtering, which is not included, which is not captured in the just by the thermal motions. So we integrate the equation of motion of dust, the relative velocity between dust and gas, which include the direct collision. The drag force include the direct collision between dust and gas, but also include the so-called plasma drag. This is when your gas is partially ion or fully ionized, you will have this Coulomb interaction between dust and gas. This actually a similar process to the dynamical friction for gravity system. And also we follow the Betatron acceleration where you have a gas compression of gas, which because of the flux freezing, the magnetic field will be enhanced, and in this case the dust will be spin up very fast, and this will also enhance the non-thermal sputtering. So while we apply this model into a single supernova explosion in a uniform medium to see how the dust will be destroyed in this case. Here I'm showing you the dust sputtering efficiency as a function of the grain size. High efficiency means that most of the dust is destroyed after the supernova explosions. So you can see that for thermal sputtering, it's actually inverse proportional to grain size because the small grains they have more surface density per volume, which promotes the collision between gas and dust. So you can see this inverse proportion relation between the efficiency and grain size. However, the non-thermal sputtering is actually quite flat. You can see this flat curve, the blue curve here, and that's because that the drag force is also has the exact same dependency as the sputtering, because drag force is all just collision between dust and gas. So this the dependency on grain size cancels out. And here there's an integrated destruction of single supernova in different environments. So this is in different ambient densities. So we're looking at the total amount of dust that is destroyed by single supernova. You can see that if you go, there's a maximum value in a diffuse phase around 0.1, and if you go to lower densities, then collision is not efficient, so the destruction goes down. But if you go to higher densities, even though you can see here that the efficiency keep increasing as you go to higher densities, the total amount of dust still goes down. And this is because at high densities, you also have more cooling, which means that your supernova bubbles will be stalled at a much earlier time. So this competition give you a sweet spot for dust destruction, which is actually a typical environment for supernova explosions, at least in the Milky Way-like galaxy. And here's an example where we apply this method into a multi-phase ISM. I'm going to show a movie of the simulation. So upper panels, you can see this is a gas surface density and the volumetric density slice and the temperature slice here. And on the bottom, you can see the dust property. This is the gas-to-dust ratio. And the inverse of it is the dust-to-gas ratio. And we separate it into carbon dust and silicate dust. And you can see this explosion of supernova is dropped randomly. And you can see most of the ISM will the ISM will be shaped by this supernova explosion into these multi-phase structures. And you can see the destruction mostly happens whenever you have a hot bubbles that is correlated with the hot bubbles. This is where most of the sputtering is happening. And already, without even including other processes, you can already see that the dust to gas ratio has some spatial variation just because of the supernova shocks destruction, and because that the turbulent mixing is not instantaneous, so you always have some variations. And we predict the destruction timescale for these two different dust species that can be used in large-scale cosmological simulations or semi-analytic models. Okay, so here's my summary. So dust evolves. So we really, not only in their abundances, but also their property can also evolve. So we just saw an example that the extinction curve will evolve in different galaxies or in different stages. And that has to do, most likely has to do with how the grain size distribution evolve as the galaxy evolves. And also the composition might change. So the composition being that what is the what kind of dust species you actually trace? Are you tracing carbon dust or silicate dust, or what kind of material form you assume? Because that will affect the sputtering rate. For example, if you assume your carbon dust is in, for example, graphite. And so recently, dust evolution has started to be included in galaxy simulations. And in cosmological simulations, these are most suitable to do like a statistic sample of a galaxy population and to study how dust will evolve across the entire Hubble time. But the limitation is the uncertainty for adopting subgrid models, where the small-scale simulations that I just described can really help to improve the subgrid model that is used for these large-scale simulations. And also observational data of dust properties, both in the thermal emissions or even in the extinction curves for different galaxy populations in different environments. For example, there's something that at low metallicities, we know that dust properties changes, the extinction properties changes, for example. And this can provide very crucial constraint for models, and we can compare the simulation to observations. So that's it. Thank you.